engineering members of the team. We're going to cover a lot of topics ranging from sort of like the basics of component design to some stuff that's more like general about racing. Oh, something's happening in the chat. Oh, great. I'm going to talk about questions in a second. So today's presentation is sort of, we're going to take a second to zoom out a little bit and look at some context behind racing itself, and like racing as sort of a sport, racing as a competition, racing as a problem, and how that sort of fits into the way that we design the car. So hopefully by the end of this, you should take away a lot of background information about sort of like what the point of racing is and what the function of a race car is supposed to be. And then Anil is going to talk a little bit more about how that fits into electric vehicles specifically, and what that looks like from sort of like an energy point of view. So hopefully it's interesting and exciting for everybody. So the way we're going to handle questions is I'm going to pause a couple times throughout my section of the presentation. I assume Anil would do something similar. And I would really appreciate it if you all would put any questions you have in the chat. And when I get to those pause points, I will open up the chat, look through the questions, try and answer them one by one. And it might be helpful if you sort of like note what slide you have the question about, so I can go back to that slide. And beyond that, feel free, please toss some questions in the chat, and I'm happy to answer them. I think Anil was trying to say something, but he might not have. His audio is not really working. He was saying that we're pretty time limited, so we're happy to stick around afterwards and answer some more specific questions, but we're going to try and move through the questions relatively quickly throughout the presentation. Awesome. So what I'm going to be talking about is sort of the problem that is imposed by racing. And I stole this title from a book called Race Car Vehicle Dynamics. But basically what we're looking at is sort of what is the purpose of a race car? And so what is the point of a race car? Fundamentally, what we want to do is we want to go around a track as fast as possible. And so some tracks like Nürburgring have really long straightaways. They have sort of like these big corners you can take. You can be going really fast on them. Other tracks are ovals, and you're sort of just taking a constant left turn the whole time. Some tracks are going through the middle of cities and have different speed requirements. Some tracks are even on dirt. But fundamentally, like when it boils down to it, even though the tracks and the vehicles that race on those tracks look different, everybody's trying to accomplish the same thing, which is to get around that track as fast as possible. And that's no different for us. So even though our track is sort of on a parking lot and made up of traffic cones, the point that we're trying to achieve as a race car is to go around that track as fast as possible. And this is especially important for SAE teams because a majority of the points that we can get at competition are from the dynamic driving events. And all of those dynamic events are scored based on your time. So they're all time-based. So what we can talk about more generally is that, yes, we want to go around a track as fast as possible, but really what that means is we want to cover a certain amount of distance in the shortest amount of time. And this is like fundamentally the problem that we're trying to solve. And so the first approach you might have to this is you might say something like what I was just saying. Well, what does that mean? How do we do that? We want to go as fast as possible. But speed and going as fast as possible aren't necessarily the right way to look at this. Top speed, or going as fast as possible as a problem, is really only true if we are measuring the top speed. What we actually want to do is we want to have the highest average speed. So out of the total track distance, we want to cover that distance in the shortest amount of time. And to accomplish this, what we want to do, and I'm going to sort of put this sentence on the board, and we're going to spend the rest of this presentation sort of dissecting the sentence, is we want to be accelerating as much as possible in the most correct direction at all times. So let's break that down a little bit. First, let's talk about acceleration. And why do we actually care about acceleration? So I'm going to sort of give a quick example here. Imagine that we're in our car and we're on some street and we want to go, we're starting at point A and we're starting from rest, so we're not moving and we're at point A, and we want to go to point B, which is some distance away. Now, if you were sort of driving in your normal car that you drive at home or whatever, the way that you would go about this will look something like this. You'd be starting at rest at time A. You would start accelerating, you press the gas, you start accelerating. You'd get up to some speed, probably the speed limit or some speed that you felt comfortable with. You would maintain that speed, sort of that constant speed for some amount of time. And then once you got close to point B, maybe somewhere around here, You would hit the brakes, and you would slow down, and you would decelerate to a stop, and then you would stop at point B. Now, the plot that we're looking at here on the left, sorry, it's kind of covered up, is a speed versus time plot. So speed on the y-axis, time on the x-axis. And an important rule of this, or we look at the area under the curve, that is representative of the amount of distance that we have traveled. So now let's compare what we just did as sort of like passenger drivers, there's like, sort of normal passenger car drivers, what a race car driver might do. A race car driver would do something like this. They'd be starting at rest at time A, at point A. They would accelerate, and they would not stop accelerating until they got to the last possible point that they could start braking. They'd slam on the brakes, and they would decelerate all the way back down to rest. Now, again, the area under this curve is the total amount of distance that we've traveled. And the important thing to take away here is that the two areas under these two curves are equal to one another. But you'll notice that the race car driver accomplished this distance in far less time than us in just sort of a normal passenger car. And so one thing that the biggest takeaway here is that when you look at a speed versus time plot for a race car, you will never see a flat line. So what I'm going to show you on the next slide is sort of an example of what a speed versus time plot might look like for a race car driver going around a whole track. So you'll see sort of the same thing I was talking about here. On this graph, there are essentially no flat lines. You'll notice that the speed is constantly changing, meaning the driver is constantly accelerating. And that's because, as we just saw, when you accelerate more and you are maximizing your accelerations, you will go around the track in less time. That is, we will be increasing our average speed over the course of the track. The only part that you see begin to sort of flatten out is when we're actually approaching the top speed of the vehicle. So the only time you'll ever see the driver going at anything near constant speed is when they're going as fast as the car can possibly go. And now on the next slide, I'm actually going to show you a real speed versus time graph coming from two different F1 drivers. So here it is, same thing, y-axis is still speed, x-axis is still time. The green graph is a Mercedes driver and the red line is a Ferrari driver. And when you look at this graph, you'll see exactly what we were just talking about. The speed is constantly changing. The drivers are always accelerating as hard as they can. And again, the only time it sort of flattens out is when we get to that top speed. So this is really important because this is essentially how you win a race. You win a race by constantly accelerating. You never want to be going at constant speed. So that'll be our first sort of section to pause for questions. Feel free to put anything in the chat, or if you have something that you feel like you can't type out, feel free just to speak up. I'll wait maybe 30 seconds for people to add some things and then keep going.
I have a quick question. When we're designing like the gear ratio and I guess the car as a whole, how are we balancing for fastest acceleration versus highest top speed?
That's a very good point. So, I mean, as with anything, it's kind of a balance. What you really want to look at is the kind of track that we're on and the kind of racing that we're going to be doing. So for a FSAE track, we're essentially never going to reach our top speed. The way that the track is laid out has very limited straightaways and you're almost always turning. So for us, acceleration is sort of much more important, especially in that sort of 0 to 60 mile an hour range. So it doesn't really make sense to have an FSAE car that has the ability to get up to like 80 to 100 miles an hour because we'll never have the time or space to do that on the actual track. But if the track was a different layout, then that might be what we're optimizing for.
Cool, thank you.
Good question. Cool. All right. Anybody else? Sounds good. I will keep going. And if something comes up, feel free just to put it in the chat. I'll check that again in a few slides. Okay. So now let's get to the next part of this sentence, which is this as much as possible piece. What does it mean to be accelerating as much as we possibly can? And really the question we need to ask here is like, what is limiting for us? What is limiting us from accelerating as much as possible? And the answer is that basically any vehicle system can theoretically limit how much acceleration is occurring. So you can imagine if we had a really, really weak motor in our car, we would not be able to accelerate forward very quickly. If our brakes were very weak, we would not be able to brake very quickly. If our accumulator was like a couple AA batteries, we'd probably not be able to output very much power and would not go very fast. So any vehicle system can always impact how much acceleration can occur. But ultimately, every acceleration is ultimately limited by our tires and how much force our tires can apply to the road. Because the only way for a vehicle to move is for us to have a reaction force from the road that gets fed through our tires and into our chassis. So we might have you can imagine a situation in which we have like the most decked out engine system ever. So imagine we had like our car and we had a Formula One, like the Ferrari Formula One engine in our car. This thing can output crazy amount of horsepower. But if our tires were made out of ice, we would not be able to accelerate very quickly. We would just be spinning our wheels. We'd be getting no traction and no forward acceleration. So I'm going to pause here for a quick terminology definition as we move forward. And this is just going to make things a little bit easier to explain. So I'm going to define two axes of the vehicle. The first one is the longitudinal axis. And the longitudinal axis defines basically the throttle, so forward acceleration and braking. So when I say longitudinal, you can think of moving like forwards and backwards relative to the car, and then lateral accelerations. And lateral accelerations are sort of our left turns and our right turns. So when I say longitudinal, I mean forward and backwards, lateral, left and right. Okay. So now let's sort of go back to this idea of what's limiting us. It might be useful for us as a team to sort of approach this problem by making a plot that represents our car's theoretical maximum acceleration. So let's sort of build this plot up from scratch. So let's look at our two axes here. The first one is longitudinal acceleration, so how much we can accelerate in the forward and back direction. And the units of this graph are going to be in G's. That is sort of like the gravitational constant for acceleration, which is about 10 meters per second squared. So this y-axis is our longitudinal acceleration, and our x-axis here is lateral acceleration. So let's define a point here, and this is if we are purely accelerating forward. So this would be, we're not turning the steering wheel at all, we're only hitting the the throttle, and accelerating forward. And let's say in our case, it just so happened that our maximum forward acceleration is half a g. So we can add that, we can put that point on our plot. Next, let's look at braking. Let's say theoretically we can brake at minus 1.7 Gs. And for turning, let's assume we can turn left and right at 1.7 Gs respectively. And so then we sort of define our cardinal points on this graph, which is representing of our car's theoretical maximum acceleration. So this is looking at purely forward, purely reverse, purely left, and purely right. It might be useful for us now to start filling in some points in between this graph. So maybe we have a point where we're both turning right and braking, a point where we're turning right and accelerating, a point where we're turning left and accelerating, and so on and so forth. And you can start to imagine that we might want to make something that basically covers our theoretical maximum acceleration in every direction. And that is what we call a GG diagram. Sorry, I kind of messed this graphic up. So the GG diagram, which let's start by looking at this sort of outer gray region, is a way for us to describe our vehicle's maximum acceleration that can occur in every direction. And this diagram is extremely useful because it characterizes for us just how much our car can accelerate in any given direction. And so the shape of this graph, again, looking at this outer gray one, is the bottom. You'll notice there's sort of two sections. There's the bottom section here and this top section that's a little bit flatter. The curve of the bottom section is defined by how much force our tires can output, like I was talking about earlier. So our tires have a maximum amount of force that they can output, a maximum amount of force that they can push our car in every direction. And so that basically defines a constant radius, and that constant radius is distributed in each direction. So if we're turning fully to the right, all of our acceleration, all of our force from our tires will help us turn to the right. Same for braking. But then we sort of begin to distribute that force into the different directions. So, and then the top section of the graph is a little bit flatter, is flatter because we're actually a rear wheel drive vehicle. So when we accelerate, we only get the benefit of two tires, whereas for the rest of the curve, we have the benefit of getting the force from four tires. So now you can imagine, say, in this outer region, this GT diagram is limited specifically by our tires. So this makes the assumption that basically every vehicle system, it can output substantially more force than our tires can output. But if we look at sort of this other example, this little red line, this is what a GT diagram might look like if our vehicle was sort of system limited. Say our transmission could not output very well, this would limit our acceleration in the forward direction. Or our brakes were really bad, this might limit our acceleration and our deceleration as we're braking. And the point here is that, oh, sorry. And so basically, ultimately, the point here is that we always want to be tire limited and not system limited. Okay. I'm going to pause here again so that we can answer some questions. Okay. How is the GG diagram made / measured? So that's a very good question. There are a lot of different experimental tests that we might want to run that would help us create this diagram. We can do, so there's 2 points. First is through system modeling. So having an understanding of exactly how much force our tires can output, having ideas of how much power our accumulator can output, having ideas of how much power our transmission can output, having an idea of how much power our brake can transmit. And so we can sort of build this diagram through understanding each of our different system parameters. And then the other half is through testing. So we can always find ways to put an accelerometer on our car and test in very isolated ways to sort of plot out the points that we were making on the diagram, like I was doing earlier, sort of like looking at a maximum acceleration case, a maximum braking case, a maximum left and right turn case. However, if we make the assumption that we are always tire limited and not system limited, we subscribe to a sort of consortium of testing that gives us information for how much total force our tires can create or our tires can generate. And so then the radius of this curve is basically defined exactly from that maximum amount of force. Okay, we have another question. Is there ever a scenario where the max acceleration is symmetrical vertically? Yes, there is a scenario in that. So if you can imagine that we had all 4 wheels being driven, so we had a motor, either our power was transmitted to all 4 wheels, or some teams do a thing where they have what are called hub motors, where there's a motor actually mounted to each individual wheel, such that each wheel was being driven and we were getting the benefit of all 4 tires. And then still assuming that those motors were always strong enough to provide more force than our tires could provide, then this graph would look like just a complete circle and not sort of that like tapered off circle. But those are both very good questions. Sorry, I can't see you, but you can give me a, oh, are there advantages of having it symmetrical? Yes, but it's more, you want to think more about the maximum amount of acceleration you can have and not necessarily about like the symmetry of it. So it would be less beneficial to have a complete symmetric circle that has a smaller amount of area than one that was larger and asymmetrical. Does that make sense? Feel free to unmute yourselves if you have like follow-up questions or anything like that too.
So are we trying to get like the biggest area or the biggest throttle or highest throttle?
So in general, you want to maximize the area. But again, it always sort of boils down to what the actual racetrack that you're racing on looks like. So if you're a drag race vehicle, like you've seen like drag racing cars where they're super long and skinny, I mean, their GG diagram looks like a huge oval. Like they cannot accelerate laterally at all, but they can accelerate forward and backward extremely high. But that's because that's sort of like the point of their race, is to go just forwards and just backwards. Cool. Anything else before I keep going?
Have we ever gotten a GG diagram from one of our vehicles?
We have not made one for one of our vehicles. We have, so things become a little bit more complicated, and I'll sort of touch on that at the end. We have sort of a sense for what this would look like for how we design for our car, but we've never like made an official one.
And it would just be like the accelerometer data that would give us that value, right?
Yeah, so again, it's like if we wanted to use one for design purposes at the beginning of the year, and say like in our case where we haven't really had a vehicle to test on, it would be more like this like suspension team would provide the numbers from our tires to the rest of the team, and the rest of the team would be able to be like, okay, here's how much we need to substantially over design our system. But then sort of the other piece of the GG diagram is for actually evaluating how good your drivers are, and I'll talk about this in a little bit as well. But then in that case, it would be coming from accelerometer data, and we would be plotting our actualized sort of accelerations versus what we think our theoretical maximum accelerations are.
Cool.
Good question. All right, cool, I'll keep going. So now let's get to sort of this last piece. And this is, what does it mean to be accelerating as much as possible in the most correct direction at all times? So as I was sort of just saying, we see a lot of different cases and a lot of different acceleration requirements throughout our race. So you can imagine sort of a straight line or a straightaway where we would want all of our acceleration to be in the forward sort of throttling direction. Or you can imagine a case where there is a sort of higher radius turn where we still want to be accelerating forward, but we need some amount of lateral acceleration for us to make that turn. You can also imagine that we might be entering into like a really tight hairpin turn at a high speed. And so we don't want to decelerate as much as we possibly could going into that corner, but then have a little bit of lateral acceleration so that we can actually begin to enter that corner. And then once we're in the corner itself, we want to be having a very high amount of lateral acceleration. But as we exit, then we sort of want to transfer into that longitudinal acceleration forwards. So you can imagine that as we're going around a racetrack and experiencing all these different turns, we would basically want to be hitting all these different acceleration requirements. And so what does this mean sort of for our overarching goal? So as I was saying before, the GG diagram sort of represents what as much as possible looks like. And this can be used as a way to evaluate driver performance. So what's on this slide right now is an actual like driver and what their laps looked like on the GG diagram. And so sort of what we can say here is that the actual problem imposed by racing can be summarized as spending as much time as close as possible to the potential that the vehicle has. That is to say, we want the driver to be spending as much time as they possibly can on this sort of outer rim of the GG diagram, because that's what our maximum acceleration of the vehicle looks like. That is what as much as possible looks like. And so you can see some interesting things just by looking at this sort of example that we have on the right here. The line, basically, this inner line represents where the driver was on the GG diagram, and it's just plotted throughout time, which is why it's a line. But the first thing we can sort of look at is see that this vehicle was like vehicle system limited, because the theoretical maximum like longitudinal acceleration is this curve up here. What we actually see is that the driver can never push past this amount of longitudinal acceleration going forward. The other thing we notice here is that the driver was like fairly cautious in braking. They were really not utilizing their brakes as much as they could have been. And so the GG diagram is an extremely useful tool for a racing team, because it basically allows them to see how well the driver is handling the vehicle that they have and how well the driver is pushing the vehicle to its maximum performance limit. So now let's look at what an ideal car would look like. So an ideal car, as we were saying before, would maximize the area of that GG diagram throughout the range of operation. That is to say that the car is providing as much potential acceleration for that race. And the other important piece of this is that the ideal car provides enough control and stability such that a driver can operate at the limit of vehicle performance at all time. You can imagine if you had an amazing car, but it was impossible to control. So say you could still accelerate in it accelerate a ton in all different directions. If it was impossible to control, a driver would never be able to push it to its limit. So I'll leave with sort of a small quote here. Historically, every major innovation in race car design has resulted in extensions of these GG acceleration boundaries and an exploitation of them through improved control or driving technique. So now I'll end with a little video here. You might want to mute your audio. I don't know how loud it's going to be. But this is one of Michigan's teams doing a lap around, I don't know where this lap is taken. But if you look on sort of the left side, oh, I get my pointer out again. If you look on the left side here of the video, I'm not getting my pointer, you'll see an actual live GG diagram plotted as the driver goes around the track. Oh, geez. All right, here we go. One quick note I will make here is that you might, if you're a keen observer, you'll have noticed that all of the accelerations are actually the opposite as how I had plotted them on the diagram before. That's because the accelerometer is measuring inertial accelerations. And so it's sort of measuring the reaction force that it's experiencing as opposed to how much the vehicle is accelerating in sort of like a global frame. And And you can kind of intuit this. Like, you can imagine if you turn a car really hard to the right, you'll get thrown to the left. The sort of same thing is being measured by the accelerometer unit. So hopefully that sort of gives you a little mental picture of what the car is actually doing. I will pause for a quick look at the chat for some questions again. All right, from Lucky. What happens when you exceed the limit of the GG diagram, such as the driver did on the left side? Okay, I'll get back to that. That is a good question. So you'll notice here on this left-hand side, the driver has sort of exceeded what we'd expect the maximum vehicle performance to be. There's a couple explanations for this. One is that, again, these are all sort of system models, and not all the models are perfect. So there are cases where, for whatever reason, the situations were such that the vehicle could exceed what we thought its theoretical maximum performance could be. However, what happens more often than not, or what's much more likely in these cases, is that the tires, when you go over the maximum amount of force that they can generate, your tires actually lose traction and they will start skidding. And so generally when you exceed the sort of exterior of the GG diagram, you'll have started slipping your tires and you will basically lose control of the vehicle. So you want to spend as much time right on this boundary, but if you try to exceed it, you will lose control of the vehicle and slide out and can often crash. Cool. And that actually sort of takes us nicely into my final point, which is a quick note on some of the GG diagrams. So like I said, they're a really useful tool to analyze the potential of the vehicle and evaluate our driver's performance. But they are not an end-all be-all, and they are not a complete descriptor of the vehicle performance. And this is because a lot of things can change how well your tires are performing. And so the GG diagram and its boundary is actually also a function of the speed that you're driving at. So if any of you sort of watch F1 or know what aerodynamic downforce is, you'll know that the faster you go, the harder your vehicle gets pushed down into the ground, and that will change how much force your tires can generate. So sometimes we actually look at GG diagrams with a third axis as speed, and that creates sort of this manifold or this envelope that looks at how well your car performs over a range of speeds. So it's definitely okay to look at it in sort of like a static case, especially for a team like us where we don't have as much of that aerodynamic downforce. And it's also so useful to understand like the average that your car will be operating at and understanding its maximum in that sense. But like I said, it's not an end-all be-all, and it's just another tool that we use to actually look at our vehicle's performance. So with that, I'll leave a couple minutes for any final questions and then point to some resources. And feel free to unmute yourself and ask a question first if you prefer. From Lucky Jordan, who's the most boomer on the team? Lucky, to your point, I'd say it's you because you couldn't figure out how to use Zoom to get the poll working. To Kay's point, how do we choose what tires to use? That's a very good question. So here's what we do. Basically, there's an amount of, the honest answer for our team is that we basically look at one website, which is Hoosier, because they make tires that are specific to FSAE students. And what we do is we use that sort of tire testing data that I was talking about before that we basically buy. And that tire testing data allows us to see how much force those tires can produce and at what speeds and like how much steering input it takes to get to those forces. And so that's sort of part of like the decisions that the suspension and chassis team makes along with like some other like high level vehicle decisions to basically decide which tire we want to use based on how much force it can produce and how often we expect to be in a situation where we can produce that much force with that tire. And so by looking at all this data, we sort of narrow down to a tire that we think is most suited to our vehicle's track will be on, our vehicle's weight, our power requirements and things like that. And then that's how we sort of pick the tire. From Owen, do we care about the tire temperature or is that only at F1 level? We should care about tire temperature, and in theory we do care about tire temperature, but we have not gotten to the point in our vehicle testing that we've really been able to characterize that in a useful way for our team. But it is absolutely something that affects your tire's performance, and it's absolutely something that's important to understand. Okay. Should the car be designed based on the tire specs, or should it be designed assuming higher values for the tire? This is a really important question. So basically, you want to design the car around the tire. There is going to be sort of an optimal tire based on what vehicle weight class you're in and the vehicle track that you're expecting to race on. And if you are designing, you basically, as I was saying before, you never want to be system limited. You always want to be limited by how much force your tires can produce. But that being said, you don't want to overbuild your system so much that you're adding additional mass or additional cost. Okay, from Audie. The GG diagram is for getting around the track the fastest. Is there an equivalent diagram / metric for optimizing with fuel consumption? There very much is, and that's actually something that Anil is going to be talking about from like sort of an electric, instead of fuel, thinking about it more in like energy consumption from a battery. Follow up, do any FSA teams use tire warmers? Tire warmers are actually not allowed per the rules, so they do not. Oh, Anil said that, sorry. I need to answer that question. Everybody's on it. Sweet. Yeah, anybody, so everybody who's asked a question, feel free to speak up if I didn't give you a satisfactory answer. Actually, let's move all those to the end. I'll be hanging around after the presentation, but we should get moving on to Anil's stuff. Really quickly, here's some resources. RCBD, Race Car Vehicle Dynamics, is a super in-depth book that covers, so basically everything that I just covered is covered in chapter 1. And there are like 26 chapters. They're all really useful to understand. I've listed some that are particularly important to this like sort of like high level stuff. Tune to Win is a much easier to digest book that covers a lot of the same things. So if you want to just like taste it a little bit, I recommend reading that. And these are both available in this, you can follow this path to, it's in our Google Drive, just follow it to the resources page in suspension and chassis. Cool. Take a quick break, like 2 minutes, grab some water, and then Neil will take us away.
Oh, Rojo, what's happening?
Yeah. Take a look at Kyle's.
Are we doing it based on age or based on personality?
Wait, what?
Can anyone see my poll?
Yeah, we can all see the poll, Lucky. At least I can see the poll.
I can't see it.
Are we doing it based on age
I don't have
or
it.
personality?
Brent, you
Definitely
get to decide.
personality. Well, you can take a number of factors.
Whatever it feels for you.
Right, guys, we can't switch gears. We only have one.
Neil, I'm glad you
What
took my
about shade?
suggestion of changing the wording there.
I don't see the
A man
poll.
beyond his age.
Can you send the poll again?
It's not gonna work.
Damn,
I've
Owen
tried
said he
3
gets
times.
boom vibes from Alex.
It's only people who joined after I relaunched mine.
Stabbed in the back
can-
by my own
Okay.
progeny.
Let's get started. I want to respect all your time. We are going to go a little over, but I promise, I hope to make it worth it. Nate, how do I move slides? Okay, so we're going to take a similar set of concepts to what Nate talked about and use a lot of the same diagrams and language, but we're going to focus on a different kind of framework. We're going to look at energy and we're going to look at power. And we're going to hopefully use those to answer some more questions, ultimately towards the same goal of how do we build the fastest race car, or how do we win? So our learning goal is to introduce this new framework, and we hope to answer how do energy and power apply to building a winning race car. A disclaimer, so I'm assuming that you're mostly comfortable with certain derivatives like distance, speed, and acceleration. I'm going to try to take a graphical approach to looking at these quantities, but I know everyone learns differently. I know Zoom makes it really hard to learn. And Nate and I are here because we love this stuff and we love to teach it and hope you guys will also love it. So feel free to reach back out to us and we will always be happy to go through it again in any different way or style. Okay, so this is the graph that Nate brought us up with, point A to point B. And we started with 2 different kind of methods of reaching that goal, each with a different amount of time and each with different amounts of acceleration. And Nate told us this mantra: we want to be accelerating as much as possible to achieve the shortest time. So I'm going to introduce two quantities. Hopefully they're familiar. The first is kinetic energy. So it has units of joules. It's calculated with 1/2 mv squared. And then the second quantity is power, which is the rate of change of energy. So energy per second, joules per second is the unit of watts. And these two equations and these two quantities are what we're going to use for most of the rest of this presentation. So we're going to look at the same example that Nate had. Your vehicle gets up to a speed, coasts for a bit, and then decelerates down back to point B. And for the sake of this example, we're going to contrive this scenario where our top speed, or the reason we stop accelerating, is limited by a very, very tiny battery. All the energy in the battery is going to turn into kinetic energy. So the battery energy is equal to 1/2 mv squared. And that speed is what's going to limit us. So if you look at the kinetic energy graph, our kinetic energy is increasing, our speed is increasing, but then once we reach the total battery energy, we're going to stop accelerating. If we look at this from a power point of view, so power is the derivative of kinetic energy. Our power is increasing and increasing until we've used up all of our energy, and it goes to 0. So in that first section, we're accelerating. The vehicle is using energy to accelerate and move. In the second section, the vehicle is coasting. So even though energy is constant, it's not changing. So the vehicle is not, you're not on the throttle, you're not on the brakes. And in the last section, the speed is decreasing, the kinetic energy is decreasing. So power is negative, and we are braking. We are losing energy from the vehicle's motion to heat and to the atmosphere in the form of brakes. So our goal is to decrease this time. And one way we could do that is to decrease the vehicle's mass. So if 1/2 mv squared equals the same thing, we can decrease the mass to increase the speed. So graphically, here's what that looks like. The kinetic energy and the power graphs are going to be basically the same. You're going to use the same amount of energy, and you're going to put it down at the same rate. But because your vehicle is lighter, you accelerate faster, you get to a higher top speed, and you decelerate faster. So this is important because reducing mass improves your acceleration, it improves your braking, it improves your turning, it improves acceleration in every direction. A second way we could decrease time is we can increase the power. We can put down that energy faster, and that'll increase our acceleration with the amount of energy that we have. So graphically, this is kind of what it looks like. The kinetic energy reaches the same level, but it gets there way faster. And to do that, you might need to put down way more power, and you reach the same top speed, but you get there faster. So as Nate was saying, the area under the curve is the same, but you do it in less time. So you can imagine this as like upgrading your motor, be able to put down more power so that instead of being system limited by your powertrain, now you're going back to being tire limited because you're accelerating at the tire's peak instead of at your motor's peak. You'll notice that this doesn't affect how quickly you decelerate because we only made an upgrade to the powertrain. So then a third example is we can increase the amount of energy we use. We get a bigger battery to increase our top speed. So you can see in the kinetic energy graph, we've exceeded what the previous cap was. In the speed graph, we're increasing speed at the same rate, so we're accelerating at the same rate, but now we reach a higher top speed. And this is the same shape of the graph that Nate had. Our power by extension is also increasing, but you can see the vehicle is constantly putting down power to accelerate or constantly taking away power to brake. And this results in what is a faster lap time. So some takeaways I hope you can get out of that section is reducing weight increases acceleration, and it does in every single direction. It takes no hardware upgrades, and you get higher performance. 2, outputting more power will increase your acceleration. And 3, increasing the amount of energy consumed will increase your top speed. So using more energy is good, putting down more power is good, and reducing weight is good. So why do we care about power and why do we care about energy? So the first thing is optimizing our vehicle's weight is extremely valuable. Every single person is designing something on this car, and every amount of weight that each part has is critical to getting this done. If we can reduce our vehicle's mass by 2%, that's huge, because the difference in time between first and second place in these events is down to the tenths and hundredths of seconds, and that's how you win. So 2, the rules define our peak power. So if you only have a peak power you can reach, then doing so in the most efficient way and with the least amount of weight means you can drive the fastest. And then 3rd, if you're consuming more energy to go faster, that means your battery pack has to store more energy, and you can't do that for free. So there's 3 costs associated with storing more energy. The first is the dollars per joule, and batteries are expensive. And the second is the weight or mass per joule. Batteries are really, really heavy and take up almost 25% of our vehicle's weight. And then the last is there's a volume per amount of energy stored, and our battery pack is huge and a huge challenge. So all 3 of these concerns are some of the biggest challenges for our team, and they're some of the biggest challenges for any electric vehicle manufacturer. So for context, some of these numbers, over $3,000 in pure battery cost, 85 pounds of just battery weight, and almost 800, I guess almost 900 inches cubed of batteries, assuming they're packed perfectly efficiently. So now we're going to talk about efficiency. And first we're going to talk about what that means. So all the energy that you put into your system must leave. At point A, you have no kinetic energy. At point B, you have 0 kinetic energy. So all the energy you put in has to be going towards your goal, towards useful work, or it's going to be wasted or lost. And we assume that nothing was wasted or lost in our previous example, but that's not true. And it's really important that that's not true in real life, and we're going to analyze that. So how are some ways that energy is lost? Well, if you went to the teaching session last week, Adi talked all about buck converters and power conversion, and how the way you design those systems can have different efficiencies. Some other common ways are electrical resistance in the terms of components, in energy conversion, in wires, in bolted joints of our bus bars. These are all things that we make decisions on, and all impact how much power is lost through electrical processes. Second, for a more mechanical perspective, is there's resistance to mechanical motion through friction, through rolling resistance in our tires and bearings, and due to the force of aerodynamic drag. And all of these things will slow you down unless you're putting down power and using energy to accelerate and to fight these forces. And then the last one is the idea that if your thing is breaking, or if it's bending or deflecting in a way that's not useful for what you're accomplishing, you're going to lose energy to do that. For example, if you push a beach ball, you're going to lose some energy into deflecting it, into squishing it, as opposed to just rolling it as far or as fast as possible. So now on the formula car, let's start with the accumulator. The important part is that the 80 kilowatt rule is measured at the accumulator, and it's measured actually by the competition judges. And if you exceed it, you're immediately disqualified. So let's look at, say its efficiency is 95%. We're transferring energy, DC power, to the motor controller. And after a 95% efficiency to the motor controller, we're at 76 kilowatts. Through some black magic energy conversion in the motor controller, that's 95% efficient, we're going to the motor. The motor gets in 72 kilowatts and is 94% efficient. Then we have the drivetrain, which we're going to call 97% efficient. And after all of those conversions and all of those lacks of efficiency, we finally get to the tires. And the tires are only getting 66 kilowatts, which is 80% of our total power, whereas the accumulator, where we're being measured, has 80 kilowatts. And every step in between is something we can design, we can choose, we can make decisions about, and making sure that the process from the accumulator to the tires in the most efficient way possible is super, super critical for making sure we have the fastest car, because the more power you can put down to the road, the more you can accelerate. In hindsight, I realize I have not stopped at all, so I will stop now. And I can scroll back any number of slides and answer any questions. Feel free to jump in over voice or in the chat.
So you said that you could like increase like power consumption. Like, how would you do that? I'm confused.
So different components have max power outputs. So we make sure that the motor is rated to a certain amount of power. The motor controller is rated to a certain amount of power. And if any of those are below like the maximum power we can achieve, then that's going to limit us from accelerating from accelerating as fast as possible. Another thing in that vein is just how good the driver is responding and controlling the car. You can think of the rate at which you're increasing your acceleration has something to do with the driver actually physically pushing the pedal and feeling comfortable and knowing the car well and being a good driver. And that's another reason that that power graph might be steeper or more shallow.
I would imagine at some point, if the car doesn't weigh enough, the downforce on the tires is like you lose a lot from having a low downforce, right? Is there a number for that, or is that something we don't really even consider because the car weighs plenty?
That's not exactly a problem that occurs with tires, because you provide more lateral force as you have more normal force on the tires because your tires are applying load through friction. However, a fundamental problem with tires is that the more load you put on them, you actually gain friction force at a decreasing rate. So you almost always want to have a lighter car, because even though yes, you're getting more like total amount of force, it's still in like a beneficial ratio as opposed to becoming a heavier car and having more force, more normal force on the tires. So it isn't really a case in which a car could be too light, except for the case of like if you were really thinking about top speed and not having enough momentum to fight things like drag. But from like a tires perspective, it's almost always useful to be lighter.
How much does the weight of the tire itself like play into all of this?
What exactly do you mean?
What's the like trade-off of having like a really heavy tire and rim or like having a really light tire and rim? Is that like independent from the weight of the chassis?
You can imagine that another way of measuring kinetic energy. So we were looking at kind of like translational energy, but there's also rotational energy. And really you should be adding those two together when you're looking at the vehicle accelerating. So the faster you have to spin, or the heavier the thing you have to spin is, the more rotational inertia it has, the more energy it takes to move at a higher speed.
Yeah, and from a suspension point of view, we talk about things in terms of sprung mass and unsprung mass. And so the wheel assembly is what we call unsprung mass, because it's not, the chassis is like sort of moving relative to your wheels through the springs. And so when your tire hits a bump, that mass is sort of moving independently of the chassis moving. And we care a lot about how quickly that like bumping action occurs, because it changes how quickly then your tire can regain contact with the road and apply force again. And so from a suspension perspective, we really want to minimize unsprung mass, because it allows your wheel assembly to react faster to inputs from the road. And so it keeps your tires on the road more consistently, as opposed to, you can imagine you had a super heavy tire and hit a bump, and that bump applies some amount of upward force. It would knock your tire up, and there would be a big lag in the system from your tire not being able to move very quickly because it's so heavy.
I see.
To answer Aurora's question in the chat, this is kind of an unclear way of displaying it, but what I was trying to get at is the accumulator is 95% efficient, and then the motor controller is 95% efficient. So you're losing energy due to resistances or switching or any of those things. And then at the end with the tires, I summed I kind of combined everything into a total efficiency and a final output for power.
And then also answering the question in the chat about drivetrain efficiency. The best way to do that is to have wheels spinning. You can actually measure the electrical power going into the motor. And then if you know the rotational inertia of the drivetrain system, you can measure how quickly the wheels spin up to speed, and you can use that to determine power applied to that system. And so you can take that power in or divide that power out by the power in to get your efficiency.
Yeah, and then Audie's question about accumulator efficiency. So if you think about accumulator losses, they're all electrical losses. So the equation for electrical power is current times voltage. And anytime you have a resistance in that current path, you're going to see a drop in voltage. So if you measure, we measure the cell voltage at the battery management system, which is right at the cell terminal. And we're also measuring voltage at the motor controller coming out of the battery pack. The current's going to be the same at both of those points because those are all in series. But if you take the power, if you calculate power both of those, because you'll have a lower voltage after all the resistances in the accumulator, you can compare power out from the accumulator to power received from the motor controller, and that's a measure of your efficiency. You could do that for any component as long as you could measure the voltage on one side and the other side of it.
You're saying that's a measurement of the accumulator and the wires between the accumulator and motor controller efficiency?
And any component in the service section, any bolted connections in the segments, anything between the battery cell and the motor controller. There's a question, what would improve drivetrain efficiency? So if you're talking purely about the transmission assembly, the choice in style, so a chain drive versus like a gearbox transmission can change your efficiency by reducing friction. Alex can talk about chain tension and how that might be wasted power. If you want to chime in, Alex.
Yeah, so pretty much this is a bit of a tricky question because what you're probably thinking is we could use belts and that would get rid of a lot of the problems we've had with chain. Belts have a whole other slew of problems, but they do solve sort of the biggest problem that we get with chain, which is that chain has a really high rotational inertia, and it also tends to make a lot of sound. And like you don't really think of sound as a way that energy leaves the system, but like the more that the chain is rattling, the more that all the components around it are vibrating, the more friction that you get between each individual link, the more energy we're losing from the system. So theoretically, if you minimized the length of your chain and the gauge of your chain, it would lose less energy than a longer chain of higher gauge. And also, every time you transfer energy from one system to another, you also lose a certain percentage of it. And so like the fewer steps between the motor and the wheels as possible is best, which is part of why teams go with hub motors. It's more complex than that, but that's part of the reason.
James, what was your question? Is something we model and test? Or Audie's question?
I was answering Audie's question.
Oh, gotcha. There's been a lot of shit posting in the chat. If I missed your question, please repeat it either verbally or at the end of the chat. Okay, cool. I just have one or two more slides. So our takeaways from this kind of section is if our vehicle is limited in power and it's measured at the battery pack, then the most efficient vehicle possible can use the most amount of that power for accelerating the vehicle and ultimately maximizing our acceleration. and almost all those components in between the accumulator and the tires is something we either choose, we design. We have lots of control there, especially on the accumulator side of things. And that's something that can really differentiate teams at competition. So another kind of angle to look at this at is like power transmission and energy storage from like a renewable energy standpoint, because it's a lot of the same concepts, but applied to a larger scale. And this might help you answer questions about why we can or can't use certain renewable energy strategies. If someone asks you, why can't we stick a giant solar panel right in the middle of the Arizona desert and power the entire country? Well, you're going to lose energy as you transmit that different distances, and massive distances it will introduce large power losses. So if you can think of these kind of concepts more globally than just an electric vehicle, but about powering your house, powering your home, storing energy and transporting energy, I think is a really powerful framework for understanding way more systems and way more types of problems than just an electric vehicle. Okay, so our final conclusion. 1, Nate loves tires. And if you haven't gotten enough about tires today, all you have to do is talk to Nate and you will learn so much. Conclusion number 2. Building a fast FSC car is an amazing optimization challenge that is impacted by every subsystem, every part, and every person. And that was one thing we really wanted to get out of this discussion from my perspective and from Nate's perspective, is that the performance of the car is way broader than any given project, any given person. Making a car go fast is not just the drivetrain and the tires and the suspension. It's the driver, it's the driver's comfort, it's the brake system, it's the weight of every component, it's how big the accumulator is, it's how good your components are. So this whole challenge is really something that all of us are kind of taking on together, and every decision that we make impacts kind of everyone else. So we hope that you can see a lot more connection between the design decisions and the things you're doing and kind of the broader framework of our team as a racing team and as this huge kind of interconnected project. And then hopefully you can think of a lot of systems besides FSE cars in a similar framework and use some of the concepts and skills we talked about today to think about new challenges and to solve new problems outside of this. That is all we have today. We are happy to stick around and answer questions. Tomorrow at the accumulator sub-team meeting, which is from 4 to 5, I believe, we will be going into, oh, Colin informed me, go to next slide. Oh, this is my outline. The feedback form. Thank you, Colin. If you would like to give us feedback, not in the next couple of minutes, feel free to fill out this form. And that'll be really helpful for not only this session, but every session in the future. Me, Nate, and Alex are planning to put together a series of sessions in the next couple of weeks about mechanical design, mechanical analyses, and as much as we can about awesome, useful skills that we would like to share with the team and to get people talking about and learning. So next week, Alex is going to be talking a lot about the fundamentals of the design process. When every week after that, we'll be building up week by week. And this form is the way we get better, the way we help you guys, the way we learn with you guys. So please take a chance to do it. I feel like that was something I was saying. Oh yeah, the accumulator meeting, we're going to dive into some more accumulator specific aspects of the energy and power design and some more technical details. So if you'd like to learn more, feel free to go to that. And then Nate and I are going to be talking with other sub-teams, the cockpit team, the drivetrain team, about extending the technicality of these presentations into more sub-team specific design challenges and design tasks and things like that. So this is definitely not the end of these concepts, but this is what we thought would be most broad reaching and most generally valuable to everyone.
Well, we'll stick around for any questions.
If there's sort of like more specific things people want to ask. Otherwise, I know suspension is also going to do a similar thing with some more specific stuff, so I can send out when we're doing that. And anybody who's more interested in some of the vehicle dynamics topics, welcome to hop on that.
Given how much the weight of the car matters, how does that impact how we're selecting the drivers, especially like for individual events?
So part of the design process is kind of giving any driver the best vehicle possible as like their platform for racing. And something I've learned through like learning about all this crap is like the quality of your driver is actually like crazy important. And like you see it really at competition and stuff like that. So if there's 5 pounds between me, Keon, if there's 5 pounds between one or the other person, but that person is 30 times a better driver than me, like that's way more impactful. But giving both of them like the best tool possible for being the best racer possible is like why we try to optimize the vehicle sans driver.
Yeah, that was also a big problem or a big challenge for the cockpit sub team, was making sure that we could choose the best drivers instead of based on size. So actually during the endurance run, you have 2 drivers, and in the break in the middle, you get like 1 minute to switch your drivers. So the end goal for the cockpit sub team would be that we could adjust our drivers so that we could put in the best drivers regardless of how big they are, because right now feasibly we kind of have to have 2 drivers of about similar sizes, because our adjustments aren't quick enough that we can get it done within the time span that we have of the driver change. But that's definitely something that we're looking at. But also, in addition with cockpit adjustability, that also, since if we have more time, it allows for us to use different size drivers for different events. So especially for acceleration, we want to have a lighter driver, because that's just straight out forwards acceleration. So then scale isn't so much of a factor, and then weight really does play a difference. So that's more of a kind of a cockpit thing of designing the ergonomics to make sure that we can adjust for the different size drivers for performance reasons.
Yeah, that was working spot on. That was awesome.
It's my one goal in life with this car, so gotta nail it.
Nate, did you have any comments on that from your perspective?
A good example of that would be oh no, I can hear me.
Oh, I can hear you.
Oh, okay. Is the show we watched for Formula Bonding, the Formula One Drive to Survive, and you can see that the drivers that professional teams pick are all over the board as far as like height or weight or whatever. But then they just like tune the cars to those people, and obviously like they don't have to switch cars per people because they have 2 whole cars, but we can take some of the same elements when we're thinking about people driving.
The note that I would make, that's another sort of part of this conversation, is, like it says on the current slide, feedback from the car to the driver is actually a super critical thing for being able to operate at the performance limit of the vehicle. And so that's something that we talk about on the suspension team. There are ways to build in more feedback coming, like pure mechanical feedback from the accelerations the driver can feel, and like how hard the steering wheel, how hard they have to be holding the steering wheel to turn. This is something we'll cover more in some like in-depth sessions, but like there are methods and mechanisms for feedback from the car to the driver that are, some are mechanical and some are electrical, like building in cockpit displays and dashboard displays that allow the driver to see real-time information from the vehicle to understand how well it's performing in certain scenarios. And that feedback is essential for drivers to be able to operate the car at its performance limit. So that's another really important part of like the driver skill weight interaction.
Lucky requested gallery view. Oh Jesus, Rohil's background has changed a lot since I last saw it.
Oh man, let's see this.
I know people ask questions about where we got the percent efficiencies for different aspects of the system. I'm gonna be honest, feel a little left out. No one asked about the motor controller. So if you're curious, it's very complicated. So we just get this equation that's a rough estimate from the motor controller manufacturer. And you can find that equation in the motor controller components page and resources. But basically, we then plotted that equation across all the ranges of current and voltages that we operate at. And 95% is like an estimate of the worst case in the ranges that we normally operate at. There are times when it's higher, like 98 or 99%. But we have to operate with the worst case assumption because that's a way we can guarantee that we'll complete endurance.
Sorry, I'm going to share my screen again.
That means leadership applications are doing what? 2 hours? Make sure to fill those out.
Aimless plug.
So this is a really cool graph that is on the data sheet for our motor controller. And it's a way more accurate description of answering the question, how efficient is our motor? Because it depends on both the speed and the torque that it's putting out. So this graph is a map of those values, which I thought is really freaking cool and way cooler than just a number. And it's true that like a lot of our systems have different efficiencies depending on how you use them. If the accumulator is putting out very, very little power, then very little of it is wasted to heating up the batteries and through voltage drops. So not every efficiency is as a number is a really, really incomplete way of describing any system.